Okay, guys, how are you? I hope all is fine, and I'm just going to share. And well, first of all, welcome you to the channel, which is Introduction to Aerospace Engineering, and we are covering the topics primarily from IIT Kanpur and other IIT institutes as well. As the time progresses, we're going to share the other data and other information, and also with the approval of the faculty members, so that we can have the sharing of the information the as per the institute demands, or as per the approval of the said professor actually delivering or actually providing the material. The purpose is just to actually create videos, just to create an awareness about an aerospace engineering, and also to share the information about B2B deals. Eventually, we are actually progressing towards creating the videos just to aware ourselves first of all, and also aware the viewers to have the connection through B2B deals as well, and else they can actually just visit our videos, and if they can have any information to be shared on, they can show with the help of the comment, and also they can like, subscribe, press the bell notification button to add in the subscription as far as the YouTube subscriber is concerned. First of all, just to have this idea, which is the Euler equations of motion, and why it is important, we have actually taken or actually produced some of the videos which were relevant to the momentum theorem earlier on. But right now what we're going to share is Euler equations of motion. We are dealing with the momentum, we are dealing with the momentum flux, the instantaneous momentum, we are dealing with the viscous fluid, we are dealing with the control surfaces, the elemental control surfaces. So whenever there is the elemental control surfaces or even the differential control surfaces, we're going to have the principle of conservation of mass applied. We're going to use the Euler's equation of motion for in three dimension, just to have the mass conservation principle to be followed. So right now in this equation, or in this video, we're going to share the principle of conservation of mass applied to an elemental control surface led to an equation, which is this one: change of momentum by time plus del into rho into v, which is equal to 0, and it is in 3D form, and where del is the vector operator and defined by this, obviously in the 3D form, I, j, and z. You can have this one as well, I, j, and k in the 3 dimensions, and x, y, and z. That is the vector operator. That will help us to actually create a matrix as well when we're going to multiply it with the v, which is the velocity vector. That will help us to actually create the matrix as well, and define the value when it will multiply by v. This would be whole which be equal to 0. Okay, that means that any physical possible flow must satisfy equation this one, which is the change of pressure with time, and also there is a momentum, density and velocity involved. So that means density and velocity combined with this one, which is change in time by p. So that would be what? That would be any physical possible flow must satisfy equation 1 at every point in the flow. For an incompressible flow, the mass density is constant, so equation 1 reduces to this one. So the equation 1 would be reduced to del of v would be equal to 0. Okay, so equation 2 is known as the divergence of velocity vector, which is div of v. Okay, this 2 is known as what? Known as the divergence of velocity vector. Which is known as div of v, shown as so 1 and 2 needs to be satisfied everywhere in the flow. Similarly, momentum theorem applied to the same element, it leads to another set of equations that must hold everywhere. Okay, so these two equations must be satisfied everywhere as well. So this is how it has been shown And with the continuation of the same concept, we have this rectangular differential control surface with delta y and delta x. P is the point with pu along the x-axis and pv along the y-axis. So we have pressure into, just taking out this differential element, the pressure would be applied on the right side, that would be p into change of p by x dx by 2. This is pv plus change of d by dx into pv into dx by 2. That is pu plus d into dx by pu into dx by 2 as well. So a rectangular differential control surface, static pressure at right face. Static pressure at right face already been shown is by this one. And because half is taken, because we are talking about half of just the rectangular, which is half the length of this. So that is why this pressure and a similar pressure on the left face produce a net force in the x direction equal to this one. And since there are no body forces present and the fluid is in viscid, the above force must equal the net momentum flux. And a net momentum flux out plus the instantaneous change of fluid momentum contained within the element. The momentum flux out of the right face in x direction would be this one. We're going to show it with the help of this equation. And right face, that would be u in the x direction, and then you're going to have multiplied by this one. Okay, so this is what is similar to what we have actually taken this one. That is because of the pressure on the left face, there is also would be a net on the left face produce a net force in the x direction equal to this one. So thus equating the net forces in x direction to the change in momentum and momentum flux, and using equation 1 leads to this, which is change of x into t, x dx by du into dx is this, and plus v into dx into dy, and that is 1 over rho is equal to change of pressure by x. That is how you're going to show the instantaneous the momentum flux first of all, and then you're going to show it with the help of this momentum flux and equation as well, which is going to lead to this one, changing it with the help of time. So generalizing this to 3D results in a set of equations known as the Eulers equations of motions. So these are the 3 Eulers equations of motion that have been driven out of what we have actually taken as an application of the rectangular differential control surface with the help of time and with the x, y, and z axis at x, v, and w. So this is how you're going to show it. Also, this negative will represent the force or the net force in the opposite direction. So notice that if u is written as x, y, z, and t, the left side of the equation is the total derivative of u. The operator this is the local acceleration, okay, and this one with respect to time is the local acceleration exists only when the flow is unsteady. In vector form, Euler's equation can be written as this one. You can write it in the vector form like this. And if the vector product of del is taken with each term in equation, this one would be like represented in the form of this is equal to 0. W is the curl of the velocity vector, and del into v, and is known as vorticity. This is known as the vorticity. So this is going to represent in the matrix form, and conclusion can be drawn from 4 for in viscid fluid. The vorticity is constant along a streamline. Since far removed from a body, the flow is usually taken to be uniform. The vorticity at that location is 0, hence it is 0 everywhere. So just to actually it will be remain uniform, and the flow would be uniform, the vorticity would be 0, so it should be taken as 0 everywhere. This is the condition. So this is how you're going to deal with it first of all, and this is how it has been shown. So W is the curl of the velocity vector, and del into v, and is known as vorticity. So normally you're going to show it like this way. These are the normal ways of showing the Euler's equation. And Euler's equation normally would be used to create a momentum flux, the instantaneous rate of momentum. As I said, when the fluid is flowing through the control surface, and when the pressure is applied in 3D form, and we're going to take it in x and y axis, just creating the equations which are like this for the pressure and for a net force in the opposite direction, which are net force in the opposite direction, and also the static pressure in this. So this would be actually shown like the static pressure and the net force in the opposite direction, and you're going to actually derive on the later equations or the Euler's equations that will help us to find out the viscosity, that will help us to find the matrix, which is del into velocity, and later on we're going to show that it is uniform, the flow is uniform, and it has to be zero, and so that it may satisfy the condition, which is this one: for incompressible flow the mass density is constant, so equation 1 is reduces to this one. Okay, so which will set us about the whole the principle of conservation of mass is being applied, and also it being observed. So with the help of the conservation of mass, and with the help of the momentum theorem, because normally it will actually, similarly with the help of the momentum theorem that we have discussed, we have applied the vector form on a surface area, so that will help us to actually create this one. Actually I have actually noted down, and we actually discussed in detail. So that was, we derived that equation, and also that one, which was for any, that one was also for an angular momentum. The angular momentum was created. There was another story, but you don't have to put the whole concept into this. This is in a separate concept, Euler's equation of motion, just to actually follow the principle of conservation of mass, and also to allow to have drive the Euler's equations of motion, just to give the viscosity, just to give the del into v into z to 0, so that we can have the all factors in concentration. So I believe that I have actually explained you. The purpose is just to give you an idea about the Euler's equations of motion, which you can actually see with the help of the law of mass of conservation of law of conservation of mass as well. So you can also apply it with the velocity vector, the del, and also you can show it in the 3D form on a differential rectangular control surface. So for another interesting video, till then, take care and have a nice day.